Hello, my name is Fenil Desai and today I will be presenting the paper Risk-Aware Graph Search with Dynamic Edge Cost Discovery (RAGS). Let's move next toward the introduction of this paper. This paper introduces a novel algorithm for incorporating uncertainties in look-ahead planning. In the domain of interest, a robot moves through an environment represented by a graph, and the true cost of edge adjacent to the robot's location are revealed dynamically. The main novelty of this work is the introduction of non-myopic graph search algorithm for risk-aware planning with uncertain edge costs and dynamic local edge cost discovery. This locally revealed information allows the planner to improve performance by predicting the edge cost revealed in the future and updating the plan accordingly in an online manner. RAGS selects the path with high probability of yielding low costs based on the probability distribution of individual edge traversal costs. This paper analyzes RAGS for its correctness and computational complexity and provide a bounding strategy to reduce its computational complexity. Further, moving towards the problem formulation for this paper, the planning scenario can be described by a graph with edge cost initially represented by some set of distributions, with the true edge cost identified as we arrive at the parent node of each edge during the path execution. Throughout this paper, the term risk in its general sense describes the uncertainty of an outcome. Consider a graph G where the cost of traversing edge is drawn from a normal distribution. The cost of path P is the sum of the edge traversal costs, each of which are normally distributed. An important implication of assumption 1 is that although multiple paths may share a subset of edges, all paths can be treated as having independent cost distributions. Given any pair of start and goal vertices in the graph, the task is to traverse the graph along the acyclic paths of least risk. The decision at each vertex can be formulated by considering the next available transition and their associated path sets. For example, say edge connection exists between the current vertex start and the vertex in next layer that are A and B. Furthermore, as seen in an image, M acyclic paths exist between node A and goal, and whereas N acyclic paths exist between node B and goal. Let the cost of each path from A to goal be drawn from normal distribution, and which can be represented by CA of I. Therefore, the lowest cost path from start to goal via A can be represented by this equation 1, where CA0 is the known cost of traveling from start to A. And similarly, the same statements can be made for node B. To traverse the path of least risk, each edge transition must select the next vertex from the next layer, such that the probability given by this equation 2 holds true. Here, Vt represents the current layer and Vt plus 1 represents the next level, which has A and B. The equation 2 signifies that transitioning to vertex V results in higher probability of executing a lower cost path than transitioning to any other vertex V dash. Now let's talk about mathematical foundations required for RAGS. Quantifying path risks. The pairwise comparison describes the probability that the lowest cost path in set A is cheaper than the lowest cost path in set B. Given assumption 1, this probability can be expanded as shown in equation 3. Each term in the integral can be represented as shown in equation 4 and equation 5. This formulation performs a trade-off between the number of available paths in each set and the quality of paths in each set. Since the derivation of function f is equal to function g, using integration by parts method, the last equation can be proved. The figure on the right shows the probability that the best path in set A has path cost less than x. The black line is plotted using mean equals to 20 and variance equals to 5. We can also note that as m tends to infinity, the function tends to 1 for all real x. This is evident by the solid curves A0, A1 and A2, black, dark blue and light blue respectively. Other trends can be observed when adding paths of varying cost distribution to the set. Here A3 includes a second path with lower mean and equivalent variance to A0. The corresponding red dotted dash path is shifted significantly to the left, causing transition towards 1 to occur much earlier. On the other hand, the addition of second path with higher mean and equivalent variance results in almost no change to the curve, as shown by overlapping yellow dotted line on the black. Adding a path with equivalent mean but lower variance results in plot purple dotted dash, which shows a much more rapid transition to 1 compared to the black line. However, the addition of a path with equal mean and higher variance increases the overall uncertainty associated with the path set, as shown by the shallower gradation of the green dashed line. This analysis motivates a bounding approach that compares the value of the path cost mean and variance to retain only the most relevant paths for the calculation of equation 3. Now let's talk about non-dominated path set. An implementation of regs requires two sweeps of the graph because an initial pass is required to gather cost to go information at each node for quantifying the path risk at execution. If all possible acyclic paths between start and goal are to be considered, then this initial pass is exponential in average branching factor of the search tree. To reduce this computation, this paper introduces a partial ordering condition based on the path cost means and variance to sort the priority queue and terminate the search. Because this paper considers costs defined by normal distribution that are evenly distributed about the mean, a path with high cost variance has an equal probability of resulting in both more or less expensive traversal. Furthermore, these probabilities are greater than that of path with the same mean cost but lower cost variance. Thus, naively penalizing paths with high variance can result in loss of optimality. In practice, the partial ordering conditions whether a path is dominated by an existing path either in open or closed set. For two paths A and B between the same set of start and end vertices, we can consider the representation of probability that the cost of traversing A is lower than that of traversing B as seen in this equation. As both paths are represented by normal distribution, that equation can be further converted to this equation. Here, the phi represents the cumulative distribution function of a normal distribution. Here, the author introduces the domination threshold, which is typically between 0.5 and 1, such that this probability is greater. Then we say that A dominates B, which is represented by this equation. The number of paths in the dominated path set grows to contain all possible paths from start to goal as domination threshold tends to 1. On the other hand, when domination threshold is 0.5, the non-dominated path set reduces to those paths with optimal mean cost. This is formalized in lemma 1 and theorem 1. From a practical perspective, the purpose of domination threshold is to determine the cutoff point for deciding which paths are included in the non-dominated path set and which are excluded. Now let's briefly discuss the pseudocode of regs algorithm. An initial sweep of graph is conducted to search for non-dominated path set, and a second sweep is conducted during execution to incorporate edge cost information as it is received. The initial sweep shown in line 1 to 17 of algorithm 1 is similar to A star procedure with three notable exceptions. First is in line 8 and 9. If the current node contains a path from start to goal, then it is included in the non-dominated path set. Second is in line 14. Each child node of the current expanded node is checked against the ancestor list to explicitly exclude looping paths. Furthermore, a child node is also excluded at this point if it is found to be dominated by any node in the closed set with the same end vertex. Third, in line 16, the initial sweep is terminated either when the open set is empty or when the next node to be expanded from the open set is found to be dominated by any node in the current non-dominated path set. The regs online execution begins by constructing the directed graph formed by the non-dominated path set on line 18, beginning at the start vertex as seen in line 20. Each edge transition first considers the set of all neighboring vertices. Here, and computes a total ordering of possible traversals according to the equation 3, as seen in line 24. It is here that regs incorporates that observed cost of the next transition if that information is available. The edge traversal is the best vertex from this set is executed, line 25, and this loop continues until the goal vertex is reached. Now let's move towards the comparison of regs algorithm with the existing search algorithms. This paper compared regs against the naive-A* implementation, a sampled A* method, and a greedy approach. Naive-A* finds and executes the lowest cost path based on mean edge costs and does not perform any replanning. The greedy search is performed over the set of non-dominated paths and selects the cheapest edge to traverse at each step. The sampled A* method searches over graphs constructed by sampling over the edge cost distribution and executes the path that is most frequently found. To provide a fair comparison, the planning time of sampled A* is limited to the time regs needed to find a path. The search algorithm were tested on a set of graphs generated with a uniform random distribution of 100 vertices over a space of 100 cross 100 units in size and connected according to the PRM star radius. Edge costs were represented by normal distribution with mean value to the Euclidean distance between vertices plus an additional cost that was generated from a normal distribution. The mean over each edge cost distribution was drawn from a uniform random distribution that lied between 0 and 100, whereas the variance was also drawn from a uniform distribution that lied between 0 and sigma max, where sigma max was tested for 5, 10, and 20, that will be shown in next slide, for each unique set of graph vertices and mean edge costs. The start vertex was defined as 0, 0, and the goal vertex was defined as 100, 100. This figure A gives an example of randomly generated graph with edge variance shown in blue-yellow scale. Darker blue line means having a smaller variance. The figure B, the non-dominated path set shown in red and the regs path is shown in black. This figure shows the resulting path cost for 100 trials over a single graph configuration where each trial drew new edge cost from the distribution as described earlier. For this set of experiments, regs used a domination threshold of 0.60 to compute the non-dominated path set. Of the 4 test path planning methods, naive A* is the only technique that always executes the same path. This is because the A* path is calculated according to the mean edge cost, which are fixed for each graph. Naive A* performs relatively well in the mean, but is prone to incurring expensive traversals. Regs is able to mitigate against severely high cost outcomes by trading off the mean and variance of available routes as well as maintaining more future path options, demonstrating the benefits of risk-aware planning. The difference between the path cost result for the greedy planner and regs shows that although the initial sweep for the non-dominated path sets can remove the most severely expensive path options, the more sophisticated decision making used in regs plan executions contributes significantly to overall success of regs. The sampled approach can account for variability in cost along the edges as long as it can sample enough paths. However, similar to naive A*, this method is also prone to risky path that yields high cost outliers because it cannot incorporate dynamic local information in the way that regs does. The collated results from 100 unique graph configurations with each graph sampled 100 times are shown in this image. In figure A, we can observe that the dominated threshold is increased. The performance of greedy planning on the non-dominated path set deteriorates rapidly. On the other hand, the performance of sampled A* improves as the threshold increases. This is largely because the computation time for regs increases as well. Regs outperforms naive A* but begin to perform poorly for larger values of domination threshold. This confirms that additional paths introduced into the non-dominated path set at higher thresholds are less likely to produce better paths. Figure B shows that the path search and execution times for each method and the total number of Monte Carlo graph required performed by sampled A stars. The computation time for the greedy planning method on the non-dominated path set closely follows that of RAGs, indicating that the majority of the computation cost is incurred during the initial sweep rather than during the online path execution. As expected, computation time of A star planning is stable and the number of Monte Carlo graphs required by sampled A star is proportional to the RAGs computation time. The number of paths stored in non-dominated path set for increasing D threshold values are also plotted against the number of sampled A star graphs in figure C. Note that all the paths in RAGs are non-dominated set are unique, whereas the sampled A star path may not be. RAGs is able to consider a significantly larger set of possible paths compared with sampled A star. Now let us discuss the satellite data experiment. Authors applied RAGs to real-world domain using satellite data. In this trial, they collected and filtered satellite images to identify potential obstacles for low-flying unmanned aerial vehicles. Useful information is extracted from the satellite images after applying Gaussian filtering to locally homogenize the images, which can be seen in figure A and figure B. Even after applying filters, this image cannot be used to provide a guaranteed cost to traverse an area due to lack of resolution or improper temporal features. Using the same method as before, authors randomly sampled the space to generate a connected graph of flight paths. To estimate the cost of the flight paths, they calculated the mean and variance of the detected obstacle pixels over each edge and used these values to characterize the edge cost distribution. This process was then repeated for every edge in the graph. For the example graph, mean and variance are shown in the figure C and D respectively, where black represents the lower value and red represents the higher value. After the edges were assigned distribution, RAGs with the threshold of 0.60 was used to search through the graph for a path from the top left start vertex to the bottom right goal vertex. Here, the threshold of 0.60 was chosen because it allows for exploration while not growing the non-dominated set to be too large. Actual values of the edge cost were drawn from the distributions as the simulated robot moved through the terrain. Authors compared the performance of RAGs with 3 other planning algorithms across 96 satellite images. The images are of field with trees of varying tree densities and may also contain houses or other built structures. Images were captured at different resolutions as well as different altitudes. Some of the results were shown with path generating using A star, RAGs and hindsight optimal paths. In figure 1, the path through an empty field are straight from start, that is magenta triangle, to goal, a cyan circle. As expected, there is a little variance in edge cost across the open field and the trajectories for RAGs and A star are identical and follows the optimal path. In figure 2, the two planners RAGs and A star again follow identical path in the presence of an obstacle field with limited options. This map results in one obvious intuitive path for the planner to find and demonstrate their ability to plan a trajectory around obstacles. In figure 3, from start to goal is blocked by large cluster of semi-permeable forest. A star executes a path through the center of the cluster that has a low cost in the mean but does not allow for easy deviations if the path is found to be untraversable. On the other hand, the path executed by RAGs demonstrates the non-myopic nature of the algorithm. RAGs executes a path that travels around the main cluster to minimize portion of the path within the dense section of the forest. In figure 4, A star actually outperforms RAGs. In this test case, the hindsight optimal path and A star path is to push to the center of the cluster along the edge with potential higher penalties, but a shorter Euclidean distance. The RAGs planner alternatively takes a path that largely avoids the cluster along a safer, although ultimately slightly high cost path. The compiled results for all the test algorithms are shown in box plot of percentage above the hindsight optimal in this figure. This states the fact that the other planning algorithms are merely searching over the single heuristic of mean traversal cost. If variance is low, then this can be enough to solve for a path that is close to the optimal solution. However, figure reveals that real-world datasets can contain significant noise, and it is valuable to account for variability during planning. Now let us talk about the hardware implementation of REGS done by the authors. The quadrotor used in these experiments is the DJI Matrice M100 equipped with a Z RGBD camera and NVIDIA Jetson TX2 development board. The quadrotor is provided a graph representation of the environment consisting of the edge cost distributions calculated from the satellite imagery of the area. It then uses either A star to plan a route or REGS to generate the non-dominated path set from the start to the finish location. The goal of the quadrotor is to fly to the finish location as quickly as possible while avoiding obstacles in the environment and follow either A star or REGS path. REGS is updated online given sensor feedback. As seen in the figure, Matrice executed different paths for REGS and A star planners. The REGS planner took slightly longer, that is 209.7 meters as compared to 201.7 meters for A star path. However, the REGS path can be seen to be less risky with fewer nearby obstacles, which allowed the quadrotor to travel at a faster speed. The Matrice was able to complete the REGS path in 162.7 seconds, whereas A star it took 174.8 seconds. Now, concluding this presentation, this paper introduced a novel approach to incorporating and addressing uncertainty in planning problems. The proposed REGS algorithm combines traditional deterministic search techniques with risk-aware planning. REGS is able to trade off the number of future path options as well as the mean and variance of the associated path cost distributions to make online edge traversal decisions that minimize the risk of executing a high-cost path. REGS has been shown to reduce the probability of executing high-cost paths over A star, sample A star, and greedy planning approaches. That was all from my side. Thank you very much.